Hello and welcome back to the continuation of the MATLAB tutorial on how we can use MATLAB to do transmission lines, impedance transformations and impedance matching networks. We've already seen on the section on how to match a complex load to a quarter wave transformer. Now we'll look at how we can do single stub matching using MATLAB. Okay. So just a refresher, I assume you know the theory behind it, which is not going to be covered here. But just to refresh ourselves, in the case of stub matching, what we do is we have a single load which is connected at the end and which we would like to have matched to the transmission line. And what is used is a combination of a stub, a short-circuited stub in parallel, connected across some length of transmission line. So the advantage as compared to a quarter wave transformer is that I don't need to come up with another different kind of a transmission line. I can just use the same transmission line with a characteristic impedance Z0 to create my entire matching network. So the two design knobs, in a manner of speaking, are the length of transmission line at which we connect the stub and the length of the stub itself. So by playing around with these two tuning knobs, the goal of stub matching is to produce a net impedance over here, Zin effective, which matches Z0. We know that when that happens, there is no reflection that comes back to the source, which is the whole point of impedance matching, right? So just to summarize, there is some length of short circuit stub, LSC, which we want to optimize. There is some length of transmission line, which we want to optimize, given a complex load. All right, so the way we will go about doing this is first we need to transform ZL by some length such that it comes back over here with some real part and imaginary part. Notice that the stub and the load are connected in parallel, so it's much more convenient to work with admittance instead of impedance. So there is some net impedance as a result of the transformation of ZL. I would like to have the real part of that admittance match the admittance that I would like to see here, which will just be 1 by Z0. We're assuming Z0 is real. And whatever is left behind, the imaginary part of the transformed admittance, should be cancelled off by the admittance of the stub across this length LSC. So those are the two steps, right? So let's get back to our MATLAB window, right? So this was the code which we had written for complex load being matched to a quarter wave transformer. So we can just continue in this. So I've written over here stub matching on a transmission line. Okay. So before we get down to writing out our solution, let's just put down the two parts, right? So part one is we want to transform the load, which is say YL, to by some length L to YL underscore, let's say T, that's the transformation, such that the real part of YL T should be equal to Y0. That is the first thing that we would like. This gives us L, right? So this is the first part of the calculation. The second part is going to be we need to calculate the length of the short circuit stub, right? So calculate LSC such that we would like to have the imaginary part of the same transformed load admittance should be equal to the negative of the, let's put it down, this is going to be purely imaginary in any case, so this is, let's say, Y SC transformed over some length LSC, right? That's what we would like, such that as a result of part 1 and part 2, we would have the net impedance, the net admittance seen from this point would simply be equal to the source circuit. Okay, so these are the two parts. So it's good to see what we would like at the end of it, right? So this should give us LSC. That's the goal, right? So let's do these two parts one by one. Now notice that since we are going to be working with admittances, it makes sense for us to define a function that returns similar to the previous case. Instead of the transformation of the impedance, we would like a transformation of the admittance. We've already done the hard work in defining the impedance transformation over here, so we don't have to rewrite this entire function for the admittance. So let's just make our own anonymous function, right? So let's start over here. Let's say function to calculate admittance, right? So I don't need to create a new function. I can just do it as an anonymous function. So I can say YL, let's call it admittance underscore transformation, right? And this is going to be a function of just one parameter, which is the length. And this is going to be 1 divided by the impedance transformation, right? Z0, ZL, beta, L, right? So this is going to calculate the admittance as a function of the length L, right? We will use this throughout the rest of the discussion. It just saves us effort because we don't have to keep taking reciprocals of the impedance, right? So this is a convenient thing. Now let's proceed. We want to equate the transformed load admittance, right? So now let's write down, again, to make life simple, let's define a y0. This is simply 1 by z0, right? This is again for convenience. So now let's begin to do, let's move this part 2 down over here. So when we start answering part 2, we'll get to it, right? So in part 1, now the next thing that we have to do is match this condition over here, right? So as before, it makes sense for us to first plot, just to get a sense of what this quantity looks like. Let's just plot it as a function of length and see what we get, right? So let's, as before, let's define the length L. Let that go from, let's say, 0 to, so lambda by, let's say, 50 as before, and lambda by 2, because we know that the impedance or admittance repeats after a length of lambda by 2. And let's calculate the YL as the transformed quantity over here. So let's write this over here as admittance underscore transformation, and let's give it the entire array, right? So now what we're going to do is, so there are previous plots which will open up over here. We don't want them to keep coming up, so let's just go ahead and comment them, okay? And let's hit run over here, right? There is a, oh, there's a mistake over here. All right. Looks like we have made a mistake. Line 35, admittance underscore transformation, length L. Missing F. Okay, so let's see. So YL underscore T has become, depending on how we did created the array for L, I've got an array created for YL underscore T. Okay, and we can go ahead and just plot this out. So let's plot L versus YL underscore T. Okay, remember that the admittance is going to be imaginary, I mean complex in general. So plotting, I must be careful to make sure I specify the real or imaginary part. So let's specify the real part first. And let's put a grid on it. Before that, make sure that it opens up in a new figure window, and we want the X label is going to be length L, right? And the title of this plot is going to be, let's just copy paste the exact quantity that we are plotting, okay? So we're ready to plot this. So I'm just going to go ahead and make this a little bit more fine. Instead of lambda by 50, let's make it lambda by 100. Okay, and let's run this over here. And let's look at our plot. Okay, so this is what the transformed load admittance looks like as a function of L, right? And now we want this to be equal to 1 by Z0, right? So 1 by Z, 50 ohms is Z0, so 1 by Z0 is going to be 0.02. So we can already see there are going to be 2 points at which this is true. All right, so as before, we can use the F0 function to find out what are those two values of length at which this is at which this condition is satisfied. All right, so this plotting that we did over here was not really necessary, but it's just to give us an intuition of what to expect. Okay, so let's create our new function, right? So let's say let's create a new function which will help us in part 1 of stub matching. So let's say let's give the function a name. Let's call it stub part 1. Okay, this is a function, remember, What does it take as input? It takes as input a length L. And what does it compute? Remember, we want to find the zeros of the function when this part 1 is satisfied, i.e. that is, this condition is satisfied. So what we should do is give it this as the function value. So y naught minus the real part of the admittance transformation, right, which is, we know, just a function of L, right? So this is the stub part, and again, to make life a little bit more easier, let's plot this out. So plot. So now we are going to give the entire function in the part 1 over here. We will give, let's give it the same length L, right, and plot this on a grid. X label is going to be as before, and the title is going to be, in this case, let's give it y naught minus this real part over here, right? Let's run this and notice, so figure 1 was just real part, so we can get rid of this. Now we have y naught minus this real part of ylt. You can see that there are 2 points over here where this function is going to be 0, and those are the roots that we are looking for. So I'm going to give an example of using the f0 function to solve this problem, but I'm going to intentionally be a little sloppy in solving it, which will show you an important aspect of how do you use the function f0. All right, so let's say we wanted this length L, which is the solution to part 1, and so I'm going to say this is equal to f0. Let's give it the function, so that's stub part 1, and let's give it the interval, right? So the interval is 0 to lambda by 2, right? Because that's what I want. I want some value of L within which this function goes to a 0. Let's run this and see, and it's going to, I'm telling you ahead of time, it's going to give me an error, right? Right. So it's produced a plot as before. So let's get rid of the plot. You can see the error over here. It says the function values at the interval endpoints must differ in sign. So at 0 and at lambda by 2, function f0 is seeing the same sign. It's a positive sign of the function. So without knowing anything else, the function is, MATLAB is not sure whether or not this function has a sign crossing involved over here, right? So this is the way in which the function f0 has been written. So it wants, when it looks at the 2 endpoints, it wants to make sure that there is a sign difference which will therefore ensure a solution to the problem of 0 crossing, right? So the simple way to solve this is going to be, notice that I should pick any point after 0, after the 0 crossing, and before the next 0 crossing. So I could, for example, pick point 25, for example, where I know that it has gone below 0, right? So this could be, for example, lambda by 4. I'm going to comment this because I don't want this plot to come up, these plots to come up anymore. So let's just comment this, right? And now when I go ahead and hit run, this is what I'm looking for. So it's given me one value over here, 0.2325, which is exactly what I had in mind, right? And now it has not complained because the sign had changed, right? And now for this value of L, I also want to know what is the actual admittance. So as before, admittance transformation at this value of L is what I want. Okay, so I can, there's another way of running this function. There's a double click over here. This has told me that the real part is 0.02. This is what I wanted from the part 1 of the solution, and part 2 is given me this, right? Let's try to see if what does the other solution look like. Maybe there is some intuition over there as well. So let's say that L is, this is computing the other part of the other solution, right? So stub part 1, let's go from lambda by 4 to lambda by 2. Okay, and then simultaneously just print out what the admittance is, right? So just, I mean, this is fairly straightforward by now. If I use the same variable L 2 times, the second time when I use it, it overwrites the value that was created the first time. Okay, right, so let's close this and let's look at what has been printed out. So it has printed out the first value, which is 0.23 meters, which is what we expected, and this is the admittance. There is a second value of L in the interval that we gave it, where the real part is the same, but the imaginary part is now a negative of this. So there is a nice symmetry over here. If one is inductive, the other is capacitive, and vice versa, right? So that tells me that there is some freedom in choosing the value of the length L over here. Okay, so that's important to keep in mind, because there's not going to be a unique solution over here. So all right, so let's just leave this as it is. Now let's go to part 2, right? So part 2 is sitting here waiting for us. Now part 2 is calculate the length of short circuit such that this condition is satisfied. Okay. So for doing this, I need to know what is the admittance of the short circuit stub itself, right? So I don't have that right now, but I should make a function for that. So let's say admittance of the short circuit stub. Okay, this is going to be a function, let's say, of one variable. So let's call it ls. Okay, and what does it do? It returns to me the admittance of a short circuited stub seen at some length ls, right? So we know the formula for this, so I'm just going to write it from memory. 1 by, it's 1j z0 tan beta L. Okay, so this gives short circuited admittance as a function of ls. Now as soon as you write this, notice there is possibly going to be a numerical problem when beta L takes a value of either 0 or pi, because at those points tan beta L is going to go to 0, and I'm doing 1 by 0. So in terms of numerical issues, this is going to give me infinity. So I have to take a little bit of care to make sure that I do not invoke this function with the values of beta L being either 0 or pi. All right, just for our sake, let's plot this out. Okay, so let's take this small length which we want to sort of avoid. Let's call it dl, and let's just call it a small quantity, say lambda by 100. All right, and it'll become clear why I'm doing this. So my first sort of instinct always is to plot a function to see how it looks. It also makes sure that my code is correct. So I'm going to choose a length of ls as an array. So I'm going to say 0 minus dl. Okay, this makes sure that the 0 plus dl. So I'm starting my calculation from slightly away from 0 in steps of the lambda by 100 as before, and I want to end at lambda by 2, but not exactly there, because once again I would run into the issue of beta L being equal to pi. So I'm going to subtract this over here. So notice this expression that I have is very similar to the way I created here. Right here I said L was going from 0 to lambda by 2, but in our case 0 and lambda by 2 are slightly problematic points. It's possible to deal with them for plotting, but we won't get into it now. So I've just, to avoid those points, I've created an offset of dl inside on both cases over here, right, on the left and the right. Now let's create a new figure for this, right, and let's plot. I'm going to plot ls versus, now note that admittance over here, this is going to give me a purely imaginary number. When I go to plot, I should give it a real number. So that real number is just going to come by taking the imaginary part of admittance, and I'm going to give the whole thing as an array, right? And of course I always like the grid. X label is going to be the length of the stub, okay, and the title is going to be the imaginary part of the short circuit admittance, right? So let's go ahead and run this once. Vectors must be of same length. Oops, looks like we've made a small mistake. Let's see, what is the error over here? Let's see. So it says that at this point, right, let's look at ls. Let's run this one by one. So I'm just going to take these two guys and I'm going to say evaluate. There's no problem over here. The mistake is over here. I miswrote the function over here. So ls is the variable, so ls needs to also be over here. Right, now there won't be any problem when I hit editor, run. Right, so the function has come out. I made a small typo in the x label. That's all right, we can fix that. So this is what we were looking at. This is the short circuit length of the stub, 0 to almost 0 to almost a lambda by 2. It starts out, the admittance starts out being negative like this, and then it becomes positive over here. Remember, by writing down imaginary part over here, I am just the y-axis over here represents the value in ohms, right? So the j part is not over here. All right, so let's just fix our little typo over here. That is a minor thing. All right, so this is what we expected. This is how the short circuit stub behaves, right? It transforms from inductive to capacitive and capacitive to inductive as I keep going along the transmission line. All right, so this is not exactly the solution to part 2. We need, for part 2, this is the condition that needs to be satisfied, right? So this was just to make sure that everything is all right. Now comes the part where I create this function which will satisfy this condition, right? So let's go back over here. Okay, so what do I need? I need yl underscore t. This is the part that I need to match. So let's say that I want to choose the length of transmission line L from part 1 over here. So let's say I want to choose the first value of L. So that means I need to comment out this part, right? So let's run this once again to make sure that we have our values correctly stored inside the variable L, right? So this is as before, the length L. So this is the target impedance over here, which is going to be imaginary part of yl underscore t, which we are targeting, right? So let's store that as some variable over here. So let's write this as yl underscore t is equal to this part, right? Or let's leave it like this. Yeah. Okay. So the value of the complex value of the admittance from this function is going to get stored in yl underscore t, and then we will take its imaginary part and equate it to the imaginary part over here. All right. So now let's create our function over here. So let's call this stub underscore part 2. And what is this function going to take in as input? It's going to take in ls, that's the length of the short circuit stub, right? Now again I'm going to be looking for zero crossings, right? So I'm going to take imaginary part of yl underscore t, that's the part I want to match, and I'm going to just use this function over here which I've written. This is what I'm trying to implement over here. So when I take it on the left hand side, this is going to be imaginary part which is going to come from the function on line 53. So this is admittance underscore short circuit as a function of ls, right? And let's close this, right? So this is exactly what we need. The first part is 0. The first part is a constant which is come from the first part of the calculation. The second part is the variable part, right? And when you look at this, this is just telling you that the net imaginary part of the admittance should be 0, so that you're only left with the real part for the purposes of creating the matching network. Okay. Now before we send this to our favorite function f0, we would always like to plot it. So our ls array over here is sort of set up, so we don't need to create it again, and I just need to create its value for the purposes of plotting. Now notice there is one thing for those of you who are new to MATLAB which might seem a little confusing. I'm using ls over here as an array. I'm also using ls as the variable to a function. All right. Now when I use ls like this over here in a function, either here or here, it's a dummy variable. I could as well have replaced ls by x or y or any other variable. It doesn't matter, right? So writing out ls as a array over here does not in any way affect the definition of this function or this function. Okay, so that's just something to keep in mind. It might seem confusing because I'm using the same variable, but it's just me being a little lazy. Let's go ahead and plot this now. So let's plot again. I'm going to, as a function of ls, I want to plot stub part 2 as a function of this ls, right? And as before, let's put a grid x label. This time we'll spell it correctly, ls, and let's give a title to it. Now what is the title? Let's just say net y, the imaginary part of y. Okay, let's run this. There we go. So figure 3 has been created. The previous figures can be closed. Now let's see what it says. So what it's saying is that as I start increasing the length of the short circuit stub, the net impedance, that the net imaginary part of the impedance, admittance, sorry, as I increase the length of the stub, it goes from a negative value to a positive value, right? So there is a value over here which is going to be the solution to our problem, right? So I already know that I'm going to get a solution. So let's just confirm it by writing ls is equal to f0. What is our function? Stub part 2. That's our function. What interval do we need to give? So it's a little tricky to give the interval as 0, because if you go in and try to calculate the value of this function at 0, it's going to see tan of 1 by tan 0, which will land me in trouble. So as before, let me just, to be on the safe side, give it, with the safety margin over here. And that's it. So that should be the solution to our impedance transformation, right? So it has given me a length of stub which is over here 0.08. The exact value is 0.0853, right? As a result of which we have got our stub matching, right? So if I wanted to in this output window have both L and LS as the solution to this thing, I don't need these plots anymore, so we can ignore them when they come. Okay, so here is the solution that we were looking for. We have the length of the stub over here is ls, which is 0.0853, and the length of the transmission line is 0.02325, right? Now if I had chosen the second value of L from here, which I've commented over here, I would have got some different value. If you want to see it just as a check, let's see if we get something else. We should get something else, so I'm going to comment this, and I'm now going to uncomment this, right? And all right, let's go and see what we get. So just keep this number in mind, that this is the first solution, and let's look at our second solution, right? Looks like there is a error that has happened. Oh yes, that happened because I didn't define this once again. Right, now it should be fine. Right. So notice that I've got the value of L is 0.37, right? And the value of LS is 0.4147. The earlier values which we had got were different. They were 0.23, now they are 0.37. The length of the stub was 0.08, and the length of the stub is now 0.4147, right? So hopefully you found this simple enough as a way of calculating stub matching, or doing stub matching without using your good old Smith charts. All right, thank you.